Hi friends, welcome to my another video. Today in this video I will discuss about the capacitor bank calculation. But before this we have to understand what is capacitor bank and what is the importance of capacitor bank in the electrical installation. If we will understand these two topics, that what is capacitor bank and what is its important in the electrical installation, the last we will discuss about how to size the capacitor bank. So what is capacitor bank? As mentioned here, a capacitor bank is a group of several capacitor of same and different rating. Capacitor bank may be connected. These capacitor means these capacitors may be connected in series or parallel to achieve desired rating. So what is capacitor bank? It's a group of capacitor which either be connected in parallel or in series to get a desired rating. If we will look the image, this is the capacitor bank panel and these all are metal encapsulated capacitor, and this as a whole it is a capacitor bank panel. Now what is the importance of the capacitor bank in the electrical installation, that we need to understand here. The capacitor bank is used in the electrical installation to improve the power factor. But here the question arises, why we need to improve the power factor. If we will understand why we need to improve the power factor, then easily we can understand that why we are using capacitor or what is the importance of capacitor in the electrical installation. So let us first discuss why we need to improve the power factor. There are many aspects to understand this topic, but I'm using here the numeric aspect to understand it very clearly. For that, I am taking one example that we need to size a generator for a commercial building which have a load of 250 kilowatt and the power factor maintained there is 0.65 lagging. So as we know that the kilowatt is equal to kVA into power factor. So kVA is equal to kilowatt divided by power factor. Then we will get the value of kVA is equal to 384.61 kVA. As we know that we should not load the generator with its 100% capacity or 100% rating. We have to always load the generator maximum to its 90% of its capacity. So we will size the generator. Generator rating will be total connected load in kVA plus 10% of the total connected load in kVA to feed this load 384.61 kilovolt ampere. So the generator rating will be 423.07 kilovolt ampere. The nearest generator available for this rating is 450 kVA. But now, as our main concern is to understand what is the effect of poor or improved power factor on electrical installation. So I will take the same example, that is a commercial building of have a load of 250 kilowatt but with the change power factor of 0.9. Before it was 0.65, but in our new example the power factor changed from 0.65 to 0.95. Now we will check what would be the generator rating for this power factor. As we done in the previous, we will calculate the kVA for this load. Then the kVA is equal to kilowatt divided by power factor. So we will get the kVA 263.15. As I discussed earlier also, we cannot load the generator of its full capacity or full rating. Always generator be loaded maximum to its 90% of its capacity. So we will get to know the generator rating is equal to 289.747 volt ampere. The nearest available generator rating is 300 kilovolt ampere. Now we will compare this to example. Before, when the power factor was 0.65, then we need a generator of 460 kilovolt ampere to feed same load of 250 kilowatt. But when we improve the power factor 0.65 to 0.95, then the same load of 250 kilowatt can be fed from 300 kVA generator. From previous two example, we can clearly see that when the power factor is improved, then the same load can be fed from 300 kilovolt ampere rating generator instead of 450 kilovolt ampere generator. It means this improved in the power factor improve the efficiency of the system, or we can say in another word that improve in the power factor will reduce the cost of the system. So what does this power factor indicate? If the power factor is 0.7, what does it mean? It's mean that only 70% of the provided power supply being used and 30% going into waste. If the power factor is 0.9, it means 90% of the power supply is used for the actual work and 10% going into waste. If the power factor is unity, it means our electrical installation is 100% efficient, or we can say in another word that the 100% of the power supply is used in the electrical installation for the work and nothing is going into the waste. Since we can say that from this discussion we can say that if the power factor is better, then the efficiency of the system is better. Now, from all this discussion, we can say that if the power factor is better, the efficiency of the system is better. So, which element in the electrical installation increase or improve the power factor? That is capacitor bank. So we can say that the capacitor bank is very important to make the electrical installation efficient because it's improving the power factor. Now let us back to our original topic, that is how to size the capacitor bank. To understand this, again I am using the numeric aspect to have a clear understanding. Let us, in our question, we have to calculate the capacitor to improve the power factor 0.65 to 0.69 for the load 650 kilowatt. So what is our question? Question is, an alternator is supplying a load of 650 kilowatt of power factor 0.65. What would be the size of capacitor in kVAR and in farad to raise the power factor or to improve the power factor to 0.95? It's very clear, means we have to calculate the capacitor bank to improve the power factor 0.65 to 0.59 if that load is 650 kilowatt. So now let us do how to calculate the capacitor size. What is the actual power factor at current? That is, power factor is cos phi is 0.65. What is desired power factor? 0.9. Cos phi is 0.95. The formula to calculate the capacitor bank in kVAR is power load, total connected load in kilowatt. In kilowatt, always take in kilowatt, never take in watt. So in formula, the capacitor bank sizing in kVAR is equal to total connected load in kilowatt into tan phi actual power factor minus tan desired power factor. We'll calculate it. If we know the cos phi, we can get tan phi from the scientific calculator. If we know the cos phi 2, that is the desired power factor, then we can know the tan phi 2, that is the desired power factor in tan form. Substitute this all values in our formula, that is P in kilowatt into tan phi minus tan phi 2. We will get the kVAR rating of 546.26 kVAR. So the nearest available capacitor bank rating is 600 kVAR. Now this rating, what we sized, it is in kVAR. We can size this capacitor bank in farad also, because we know the capacitor SI unit of capacitor is farad. So let us calculate the capacitor bank's rating in farad units also. So there is a formula for this to calculate the capacitor bank rating in farad, that is kVAR in divided by 2 pi f into voltage square, where f is frequency, that is 50 Hz, and V is equal to 415 volt, because all the system we discuss here in example, it's 3-phase. So let's put all this value in this formula. kVAR, which we calculated earlier, it's 546.26. so we substitute this value here. 2 into 3.14 is a pi value, F is 50 Hz, and voltage is 415 volt. This is voltage square, so we multiplied it 2 times. When we will calculate this, we will get to know the farad value, that is 101.01 microfarad. Hope you enjoyed this video. We will discuss in any other video.